What I want to talk about today is how we can take some new approaches to do things like rewire how we actually heal tissues. And so diabetes, obesity, and old age all lead to an inability to heal wounds. And this is leading to something called the silent epidemic. And so this is because survival is fundamentally linked to the ability to heal damage to our skin. And by creating a formidable barrier, it keeps us safe from infections that would otherwise be fatal. And so globally, non-healing ulcers on diabetic feet lead to an amputation about every 30 seconds and have lower 5-year survival rates than breast and prostate cancer. And so with the incidence of diabetes predicted to increase over 50% in the next 20 years to 640 million people, this is a rapidly growing global epidemic. And the cost of treating these wounds is quite staggering. $17 billion is spent in the US alone, which equals the direct healthcare spending on breast cancer. In other countries, treating a single ulcer can consume 6 years of personal income. Here in the UK, approximately 1 pound of every 150 pounds of NHS spending is spent treating these diabetic ulcers. And so this is money that is better spent on preventing and curing diseases rather than treating a complication of one. And so, despite diabetes consuming over $800 billion international dollars, and diabetics with ulcers being twice as expensive to treat, attempts over the past 20 years to develop drugs to heal these wounds has produced a graveyard of failure. And the reason for this is that healing our wounds is one of the most complex biological processes that our bodies must perform. And so following wounding, different cells work together over time in a coordinated fashion to heal the damage, similar to musicians in an orchestra. And so therapeutic strategies that are designed to target only one of the many problems in this complex process are very unlikely to be successful at promoting healing. But the question is it possible to design a therapy that acts like a conductor in an orchestra, instructing multiple players on when, where, and what they need to do? And so my research group looks at designing dynamic biomaterials that rewire the process of wound repair over time. Historically, materials have largely been passive players in tissue repair. They serve as band-aids or supportive scaffolds, but lack the ability to actively direct repair. But tissues are fundamentally dynamic. They respond to changes in their environment. And so what we need is a way that we can actually interface therapeutic materials with tissues over time. So my approach combines aspects of material science, DNA nanotechnology, self-assembly, and additive manufacturing to design materials that actively coordinate biological processes. This allows us to design materials that actually act like a conductor, actively synchronizing the process of repair. And so, for instance, they do this by concentrating key therapeutic molecules found within the body and then subsequently activating them at various stages during repair. They also deliver therapeutics that rewire how cells interpret instructions, making them more likely to heal. This is a fundamentally different approach to therapy. It recognizes that there's inherent spatial and temporal dynamics that are critical to successful healing. But it also requires an understanding of the key barriers to healing at each time point during the process of repair. And so understanding what these barriers are takes a wealth of diverse knowledge. And so I'm working with clinicians to uncover what the local biological defects are within diabetic ulcers that prevent them from healing. I'm also working with biologists to understand how natural biological variation between individuals gives rise to a differing ability to heal wounds. These insights can then be combined to program specific therapeutic combinations and sequences into my materials. And then these materials can be applied like a Band-Aid, but unlike a Band-Aid, they orchestrate the process of wound repair over time. But the materials are only part of the story. The insights used to program these materials may also be used to identify the patients that are most likely to develop these chronic non-healing ulcers. And this may lead to the potential to create personalized, comprehensive treatment programs that drive efficient healing. But identifying what the key barriers are that lead to an inability to heal is a formidable task. But recent advances and new advances in things like artificial intelligence and neural networks provide an enticing opportunity for predicting on a personalized level what treatments are going to lead to healing. And so the capability to take large data sets and predict how they impact complex signaling networks provides a revolutionary ability to actually be able to take and design personalized therapies to treat individual wounds. This can then be combined with smart bandages that actively monitor the local wound environment and give out a reading of exactly what treatments are necessary to promote healing. But these materials and these insights are really only useful if they reach the clinic. And so recently I've started working and establishing collaborations with industrial partners to drive these towards the market. Because if they get there, they have a potential to treat a variety of damaged tissues throughout the body, not just diabetic ulcers. But the path to market is still an uphill climb. While I'm fairly confident that innovations like this can reach the market in 20 years, they're really something that's needed now. So if you look at things like cancer, they have combination therapies that allow you to treat in a much more effective way. But in a case of something like wound healing, we lack the ability to use these advanced techniques and these advanced combination therapies, despite them having lower survival rates than several cancers. And so it's an area that we're really interested in, and hopefully we'll see many advances significantly before 2037, but definitely by then. Thank you.
Great. Thank you very much. Thanks, Ben. Interested, just particularly asking you, the challenge you got, I can see, is you've got an extraordinary technology or approach that's developing, but the challenge is getting this scaled and to market. I mean, what's the main barrier that you're finding? Is it that people don't get it, or what is it?
Yeah, so there's several barriers. So something in application like diabetic ulcers, one of them is that they're extremely heterogeneous. So actually being able to identify and stratify patients and figure out what's going to work for individuals is a big challenge. The other one is, as you add complexity into treatments, the pathway through regulatory bodies to actually push these through becomes extremely complex. So a lot of the more complex therapies aren't attempted simply because there's not a clear regulatory pathway to actually push them to market.
Right. Is there also a resistance to some of this? I don't know, vested interests sort of saying, you know, what we do is what we do, we occupy this territory, so actually these sort of new ideas, we don't really like them? Or? So
one of the big problems in pharma is actually being able to deliver effective therapies. And so they've developed tons of small molecules, many of them which are inefficient at delivery. But also speaking with representatives from pharma, there's an appreciation that combinations and more complex therapies are more effective, but they're too risky in terms of investing resources in them to try to get them through.
Right. And you don't fancy embedding yourself in big pharma, actually being part of a major corporation?
Not myself, no.
Okay. Maybe one of these days you will become that big corporation. I gather you're giving this presentation at the World Economic Forum, is that right?
A slightly different version, but.
Okay, just tell us about that. That's quite a big platform to offer some insights on.
Yeah, so it's going to be an interesting opportunity to really get together leaders from business and policy and government to begin to ask, how do you actually take some of these more advanced technologies? Because the engineering and the science behind it that we can drive from the academic side and from the industrial research side is at one level, but then we need to work in terms of the global ecosystem on how you actually then translate these and what new pathways there needs to be to actually get these to market.
Right, okay. Well, Ben, we wish you all the very best. We'll have you back on the platform in a short moment, but for now, thanks very much indeed. Great.